Hi everyone, I'm Han Yan. Welcome to our talk, BrokenMesh New Attack Surfaces of Bluetooth Mesh. In this talk, we will discuss some common attack surfaces and vulnerabilities of Bluetooth Mesh technology. First, let me introduce our team. We belong to the Baidu AIoT security team. We now focus on the security of Android and the Linux platform, and our duty is to discover zero-day vulnerability and explore possible defense solutions. In this talk, we will first introduce some basic concepts of Bluetooth Mesh technology, and then we will analyze the attack surfaces to show where to attack, when to attack, and how to attack. And next, we will introduce BLE Mesh Fuzzer, an automated fuzzing tool for Bluetooth Mesh, and show its effect with several case studies. Well, let's start with the Bluetooth Mesh technology. Bluetooth Mesh is also known as Bluetooth LE Mesh or BLE Mesh. It is a wireless mesh networking technology based on BLE. Bluetooth Mesh was made public by SIG in 2017, and now is widely used in smart home and industrial IoT and other things. When hearing the Bluetooth Mesh, maybe one of the most confusing questions is, what is the difference between Bluetooth Mesh and the Bluetooth Classic or Bluetooth LE? We think the main difference is that Bluetooth Classic and BLE are wireless communication technology. They are just like Wi-Fi, while the Bluetooth Mesh is a networking technology. It's just like the TCP/IP. And this figure shows their protocol stack. As we can see, Bluetooth Mesh has a network layer, but the other protocol do not. Since Bluetooth Mesh is a networking technology, communication in Bluetooth Mesh is no longer just point-to-point. A large number of devices forms a network and communicate with each other. Formally, device in the mesh network is called node, and you could see there are many types of nodes, but we only need to focus on the basic node and the relay node here. Okay, let's see how the message flows in this network. Assuming that the node A wants to send some message to this node E, it can just pass the message to the relay node Q, and the Q will then forward the message to E. In this process, node A actually advertises the message to all the nearby nodes, include the node B, node Q, and node P, and so on. But only the relay node Q will do the forward job. And we call such communication mechanism as managed flooding. We have figured out how message flows, but how to represent the source and destination of a message. In fact, just like TCP/IP, each node in mesh network have a network address. There are basically 4 types of address, but we can focus on 2 of them. The first is unicast address. It is an address for each individual node. And the second is the group address. It is an address for a group of nodes. And in this example, node B has a unicast address, while node C and node D has the same group address. So node A can send message to node B just by its unicast address, and node A can send a message to C and D at the same time by their group address. Let's further understand the Bluetooth Mesh communication from a higher level. Bluetooth Mesh adopts message-oriented communication, which is also known as publish and subscribe. Here, publish means sending message to a specific address. A node can publish message to unicast address and group address. While subscribe means start to receive message with specific destination address. A node can subscribe to a group address. We also see the example. These slides have subscribed to the group address keychain, while this switch can publish an on message to the group address keychain to turn on those slides. So, in summary, Bluetooth Mesh is a networking technology based on BLE, and the nodes can communicate with each other in the network. Okay, in the second part, we will analyze the attack surfaces of Bluetooth Mesh. Our research scope includes two aspects. The first is protocol, and the second is wrapper application. Here, the protocol means Bluetooth Mesh specification, which is proposed by SIG, and wrapper application means software framework for providing Bluetooth Mesh capabilities to upper layer applications. And further, we divide the protocol into two key stages. The first is network build stage, and the second is network control stage. On the other hand, in this research, we focus on software implementation vulnerabilities of Bluetooth Mesh, such as memory corruption. Well, let's start with the network build protocol. Network build is a process in which new devices join the mesh network with the help of a mesh gateway. Formally, the network build is called provisioning, and the mesh gateway is called provisioner, and the new device is called unprovisioned device. Network build protocol contains file procedures, but we just need to know the overview. That's okay. An unprovisioned device first sends a specific beacon to the provisioner to announce that I want to join in the mesh network. And provisioner then build a link with the unprovisioned device. And then both of them provide some necessary information to each other. And here is a critical point. The provisioner and the unprovisioned device will calculate a shared key using ECDH algorithm and use the shared key to increase something for authentication. We should notice that the authentication is often based on some vendor-specific parameters, which means that a device of vendor A may not be able to join the mesh network through a provisioner of vendor B. And finally, the provisioning is done. Unprovisioned device will send a link close to the provisioner to end this link. And also notice that if provisioning fails, provisioner can also send a link close to unprovisioned device. Next, we need to take a further look at the provisioning message format. In fact, all the message used in provisioning follows this format. We can see the whole packet is just a Bluetooth low energy advertising packet, which means that the Bluetooth mesh is actually built on top of the Bluetooth low energy. And the data related to provisioning are all here in the generic provisioning PDU, and especially in these two, in the transaction start PDU and the transaction continue PDU. So how the mesh protocol implementation pass the generic provisioning PDU is the key point of vulnerability mining. Okay, let us see the attack surfaces of the network build stage. First, we need to decide when to attack. We think the attack should be carried out before the authentication, because in these procedures, no extra information is required, so the attack is applicable to any vendor-specific device. And next, we need to decide what to attack. And after our study, we found that the segmentation and reassembly mechanism is a perfect target. The segmentation and reassembly are designed for transmitting extremely long data. It is realized through these two, the transaction start PDU and the transaction continue PDU. Here, the transaction start PDU is the first segment, and the transaction continue PDU are the remaining. We consider the segmented and reassembly as perfect target because it is a general mechanism so that supported by all the mesh devices. Meanwhile, receiving and caching segmented packet involve memory operation, which are very likely to cause memory corruption. So we can attack the segmentation and the reassembly by mutate length-related fields of transaction start PU and the transaction continue PU. The fields are SEGN, total length, and the segment index. And we will show an automated fuzzing tool for this purpose later. Okay, in summary, the threat model of a network build attack surface are shown here. The attacker can be either a provisioner or an unprovisioned device. For by the provisioner, it can send malformed segmented packets to victim unprovisioned device after building link. And the vulnerability will be triggered on victim during its reassembly. And similarly, a bad unprovisioned device can send malformed segmented packet to the victim provisioner after receiving the provisioning invite. Here. Okay, next, let's see the network control protocol. Network control is a process that one device sends message to other devices. For example, a switch can send some message to the lights to turn on those lights. We call it network control. And the network control protocol follows a layered architecture, and there are totally 8 layers. Here we can just focus on the network layer and the transport layer here. In network layer, there are network address, including the source address, SRC, and the destination address, DST. And in transport layer, or more specifically in the lower transport layer, there are fields designed for the segmentation and reassembly. Well, yes, the network control also supports a segmentation and reassembly mechanism. The Bluetooth Mesh natively supports some security features, and one of the main security features is the message obfuscation and encryption. In Bluetooth Mesh, there are 2 keys for the encryption, and they are known as NAT key and APP key. The NAT key is used to obfuscate and encrypt fields of network layer here, and the APP key is used to encrypt the fields of upper transport layer here. And in consequence, if we have no keys, we can only know the IVI, NID, and the NAT MIC here because they are in raw. But if we have the NAT key, then we can pass the whole network layer and the whole lower transport layer. And if we have NAT key and the APP key, we can pass the whole message. Okay, next, let's see the attack surfaces of network control stage. Similar to the network build stage, we found that segmentation and the reassembly mechanism is an ideal attack target in the network control stage. In addition to the reason that it is a general mechanism and involves memory operation, it is also because that the segmentation and reassembly occur in the lower transport layer, so that only NAT key is required, not APP key. But why is this an advantage? We need to know that all the devices within the network have the same NAT key, but different devices may have different APP key. As long as the attacker joins in the mesh network, the NAT key can be obtained. It means that the attacker can send malware message to any other device. And we can also attack segmentation and reassembly by mutating the length-related fields, such as this control, SEGO, SEGN, and the segment I'm here. Well, the threat model of network control attack surface is shown like this. From this threat model, we can see in Bluetooth Mesh, the attack vector is no longer limited to the adjacent. The attacker device A can send the malware segmented package to nearby victim, the device C, and it can also send to remote victim device D with the help of the relay node F. So vulnerabilities will be triggered on victim during the reassembly. Okay, we have finished the attack surface analysis for Bluetooth Mesh protocol. And finally, let us find out the attack surfaces of Bluetooth Mesh wrapper application. First, we need to define what is a wrapper application. This figure shows a typical framework of Bluetooth Mesh in Android. The mesh capability are wrapped as AIDR service provided by this process called the Android Bluetooth. Other Android app can utilize these capabilities through the AIDR bundle. For example, an Android app wants to send a mesh message. It can just call the corresponding interface provided by the mesh service, and the mesh service will then forward this call to the GNI layer, and the GNI layer will then forward this call to the hall layer, finally to the livemesh.so. Well, the livemesh.so will send the HCI command to Bluetooth chip to actually send the mesh message out. Assume that the attacker is malware Android app and the attack vector is the malicious call. Then from this architecture, we can see there are two main attack surfaces. The first, we can attack the permission restriction of AIDR service. We can try to call the mesh service without Bluetooth permission. And second, we can attack the memory operation in GNI and hall layer. These two layers are often implemented using C or CPP, which are very likely to involve memory corruption vulnerabilities. So we can try to call the mesh service with malformed parameters to see what happens. So in conclusion, permission restriction and memory operation are two main attack surfaces in wrapper application, and we will show more details in the case study part. In third part, we will introduce BLE Mesh Fuzzer, a fuzzing tool we designed to find the vulnerabilities in Bluetooth Mesh protocol implementation. And our goal is to fuzz both network build and network control stages so that the BLE Mesh Fuzzer is composed of two corresponding subsystems. Here is an overview of the network build fuzzer. For fuzzing process, there are several necessary things to do. We need to generate test cases, and we need to send them to the target device and monitor the response from the target device to detect crash. So BLE Mesh Fuzzer also follows this framework. For the test case generation, we define a series of segmented packets as a single test case, like this. And we generate them at once in each fuzzing loop. Then our sender will first follow the normal provisioning procedure to build a link with the target device. And when it's fuzzer's turn to send message, our sender will send each packet of test case to the target device. Meanwhile, we monitor the response from the target device to detect crash. If fuzzer do not receive the link close from the target device, which is expected to receive after a time interval, and we will consider it as the crash happening. By the way, monitoring log from serial port is also a way to detect crash, but different developer board may have different output, so it may take more effort to adapt to each vendor. So in the contrast, The link close-based crash detection method is more general. And these two sequence diagrams show how the network build fuzzer works. The first diagram shows the case that trigger vulnerability. At first, the fuzzer will generate a test case, which is composed of several segmented packets. Then the fuzzer follows the normal provisioning procedure, builds a link with the target device. And when link is established, the fuzzer starts to send segmented packets, as well as wait for the link close. Assuming that this transport continue PDU triggers vulnerability, causing the target device to crash, then the target device will lose all the information for this provisioning session, so it will never send the link close to our fuzzer. And we return to the fuzzer side. The second timer has timed out, and the fuzzer does not receive any link close. So the fuzzer will consider it as crash happening, then save the crash log and clear the timer. Well, the second diagram shows the case that not trigger vulnerability. Assuming that this segmented packet is determined as invalid by the target device and cause a check fail, and the target device sends the link close to the fuzzer due to the check fail, then the fuzzer knows that this fuzzing loop has failed, so just reset the timer and start the next fuzzing loop. Now we have established a fuzzing framework, so the last work to do is to define how to generate the test case. A test case is composed of one transaction start PDU and n numbers of transaction continue PDU. When generating the test case, we first randomize the package count 1 plus n, and then we random the SEGN total length data length of the transaction start PDU, and we randomize the SEGO data length of the transaction continue PDU to form a test case. And this is an example. The fuzzer has generated parameters such as SEGN, and this test case finally caused the target device to crash. Okay, let's move to the network control fuzzer. Network control fuzzer is also composed of 3 main modules: the test case generation, sender receiver, and the crash detection. A test case is also defined as a series of segmented packets. And our fuzzer will send these segmented packets to the target device one by one. And notice that the sender will also send some probe packets to the target device at the same time. Here, the probe packets are valid segmented packets, and they are used to detect the crash. In normal case, target device will send ACKs to the probe packets. An ACK packets contain response to multiple probes. This is called the block ACK. And if fuzzer finds that some ACKs to the probes are missing, then the crash is considered to happen. By the way, why we need the probes rather than just monitoring the ACK to test case to detect crash? This is because that missing ACK to test case may be caused by a crash, but it may also be caused by the invalid packet not being accepted. It is just hard to tell these two situations. But for the probe, missing ACK for probe must means crash. So it's a better indicator. And these two sequence diagrams show how the network build fuzzer works. The first diagram shows the case that trigger vulnerability. At first, fuzzer also generates a test case, which is composed of several segmented packets. Then the fuzzer sends the first packet to the target device, as well as the probe. And we can see that the target device responds execute to both segmented and the probe. That's correct. And next, the fuzzer sends the second segmented packet, but this packet is not accepted by the target device. So no execute to this packet will be sent. But we do not care. That's okay. And the fuzzer received the execute to the probe. So we know that the target device works fine. And then the fuzzer sent the third segmented packet and trigger crash on the target device. And next, fuzzer send probe to the target device. And now is the critical point. If the mesh service on the target device is permanently down, the fuzzer will find that the execute to the probe is missing, so that no crash has occurred. This is the simplest case. But even if the mesh service is not permanently down, we can still detect a crash. Because when mesh crash, all the information about this segmentation and reassembly session has been lost. So this ACK will only respond to the last probe, but missing the response to the first and the second probe. So if we found the missing, we know that the mesh service on the target device has crashed. Well, for the case that not trigger vulnerability, fuzzer will receive all the ACKs to probe and know that nothing happens. The test case generation is similar to the network build. We first decide how many segmented packets are included in a single test case, and then we randomize the SEGN, SEGO data lines and control. These fields are related to the lines. And here is an example. The fuzzer has generated several concerned parameters and finally triggered the target device to crash. Okay, this is the last part of our fuzzer. We implement our system based on the Nordic NRF module, and this module supports the sending and receiving of Bluetooth signals. And in the aspect of software, since the Bluetooth mesh is built on top of Bluetooth low energy, so we need to find out a tool that can send raw BLE packets first. And here we utilize the SwingTooth driver for this purpose. SwingTooth is a great open source tool that allows us customize the BLE via Python. And thanks for their great work. And next, we implement the mesh protocol based on the mesh spec. And this is a code snippet that shows the details of network layer. And finally, we implement our system based on our self-implemented protocol. The fourth part is about our real-world vulnerability mining of Bluetooth mesh. And up to July 24, we have found a total of 17 issues, covered 8 well-known vendors and obtained 13 CVEs. And now all the listed CVEs have been fixed by vendors. In this part, we will discuss the vulnerabilities in network build stage, network control stage, and the router application. The first case is an out-of-bound write vulnerability in network build stage. Here we need to know two fields, the SEGN and the total length. And the SEGN means number of segments. It is a zero-based value. For example, the SEGN equals 3 means that the whole message is divided into 4 segmented packets, while the total length means the total number of bytes in the whole message. In a valid case, SEGN and the total length should be matched. For example, if total length is 65, then the SEGN should be 2. Which means that 65 bytes are divided into 3 segmented packets. Okay, This is a vulnerability that the Mesh SDK allows mismatched SEGN and total length in the network build stage. And in this case, the attacker first sends a transaction start PDU to the victim with the total length 65, but with the SEGN 30. And the victim first picks up the total length. Okay, it's 35. So victim will allocate a 65 bytes buffer to cache all the segmented packets. But next, the victim will pick up the segment, the SEGN is 30, and it will consider that there are totally 31 packets to receive. In fact, that is incorrect. So the attacker can just need to send a mail from the segmented packet whose segmented index is 3. And here, since the segmented index 3 is smaller than the SEGN, so this packet will be cached and will be considered as valid. But the segmented index 3 means that this is the fourth packet. So this packet will be caching here and finally leads to the out of bound write. Here is the POC. We first build a link with the victim and then send the mail from the segmented packets. And this finally leads to the crash of my service. Okay, the second case is an out of bound write vulnerability in network control stage. Again, we need to know these two fields, the SEGN and the SEGO. SEGN is also the number of segments, and SEGO is similar to segment index in network build protocol. It is the offset number, indicates which segment the current packet is. And in valid case, for certain segmentation and reassembly session, the SEGN in all the segmented packets should be the same. But in this bad case, Mesh SDK allows the SEGN to be inconsistent. Here, the attacker first sends a segmented packet to the victim with the SEGN 1 and the SEGO 0. That's okay. It means that there are two segmented packets in total, and this is the first one. And the victim will pick up the SEGN. Well, since there are totally 2 packets to receive, it just allocates a buffer for these 2 packets. But next, the attacker will send a mail from the packets with SEGN 31 and SEGO 2. Victim just do a check that the SEGO here is smaller than the SEGN here, and incorrectly consider it as the valid packet and cache it into buffer. Again, since the SEGO is 2, this packet is considered as the third packet. So this packet will be cached out of bound and finally cause out of bound write.
5 minutes, Mr. Han, 5 minutes.
This is the POC. We just changed the SEGN of different packets, and the first is 1 and the other are 31. This finally leads to crash in victim device. And from the log, we can see we can hijack the PC and R0 so that this crash can lead to remote code execution, RCE. And now we are clear about the vulnerabilities in Mesh protocol. Next, let's see what happens in the regular application. The first vulnerability is a permission leak in Mesh service. It is discovered on Android platform. Although the services have some permission check, but it treats all the foreground application as permitted caller, so that every application can call the service interface, even they do not have any permission related to Bluetooth. And here's the POC. An untrusted app without any permission can successfully call the mesh service. Of course, this vulnerability is an entry, and more vulnerabilities can be triggered by calling the service interface with malformed parameters. And here is an example. This is a Stack Overflow vulnerabilities in Bluetooth Mesh GNI. And in Bluetooth Mesh service, there is an interface that receives an array from the caller. That array is passed from GNI layer, from Java layer to GNI layer, and copied into stack. The vulnerability is that the memory copy doesn't check the length of array. So if user passes an overlength array to the interface, it will cause the stack overflow. In the end, we summarize our work as follows. From the study, we know memory corruption vulnerabilities are very likely to occur in the segmentation and reassembly implementation. And the security of wrapper application, especially their permission and native, also needs attention. And all the listed CVE have been fixed by vendors. For the framework, we plan to enhance our fuzzing system and feedback-driven fuzzing strategy. And our starting now is concentrated on the network layer and the low transport layer. In the future, we will do vulnerability mining at upper layers. And also, Bluetooth Mesh has a lot of interesting features, such as GATT proxy. We could explore the attack surfaces of GATT proxy protocol. In the end, we hope our work can help to improve the security of Bluetooth Mesh. Thank you for listening. Any question, please tell me, and you can also contact with me on the Skype card. Thank you.